So in this case, we want to use an analytic way to determine that this sequence is decreasing. So we have to do this in a way that, in a universal way, in a way that works for every single term, and like the first and second, not by plugging in numbers, because that to exhaust is simply not feasible. So this is what we're going to do. So we know that a sequence will be decreasing if a sub n is greater than a sub n plus 1. Okay, so let's write down that condition. So decreasing if a sub n is greater than a sub n plus 1. That is, the next term in the sequence is smaller than the previous term, all right? So we need to define a sub n, which, by the way, a sub n is given. That's n over n squared plus 1. And, we need to determine a sub n plus 1. That is, we are going to shift every instance of n in the original sequence with n plus 1. N plus 1 over n plus 1 squared plus 1. So we got both the a sub n and the a sub n plus 1. So we're going to set up this inequality. That is a sub n greater than a sub n plus 1. In other words, n over n squared plus 1. Is that greater than n plus 1 over n plus 1 squared plus 1? Is this inequality true? It is true because, even though in the numerator we have an n and an n plus 1 on the right hand side, that should be then bigger than n. However, it is actually the denominator on the right hand side a quantity way larger than on the right hand side, because this n plus 1 squared, for example, so n squared plus 2n plus 1 plus 1 plus 2. Well, this quantity is for sure bigger than n squared plus 1. So that denominator on the right hand side of the inequality should be bigger, and therefore that's going to give us a smaller quantity. All right. So in this case, this is how we show that in this case it's decreasing or increasing depending on the case. All right, so we chose this time to do a decreasing sequence. Okay, so sequences can be bounded and can either be bounded above or bounded below. And that bound, if it's an upper bound, it's denoted some big M. But otherwise, if it's a lower bound, it's denoted lowercase m. So in this case, this happens usually when sequences are monotonic. They're decreasing, for example. Never mind about that. So we can have a limit above, or limits below, or limits both above and below. So whenever we have a sequence that is both bounded above and bounded below, we just say that the sequence is bounded. We don't need to say it's bounded both above and below. All right. So let's look at this couple of examples and determine whether this sequence is or rather check the boundedness of the sequence to determine whether they're bounded above or bounded below. So all we have to do is find the limit of the sequence, and we already did a few examples on finding limits of sequences. So that's a 2e to the negative n over 3. And what happens at infinity in this case? Oh, it's plus, not. Actually, there's a little typo. That's supposed to be 2 plus e to the negative n over 3, not times, all right? It's a little typo there. And so where is this term going to go? The second term, the exponential term, where is it going to go to for large values of n? What is that? Anyone? This term, where is that going to go for n really big? 0, right? So the limit will be 2. All right. So here is the thing. In this case, we would need to look at the graph of the related function. In this case, what do we have? We have an exponential function with a negative exponent. That means that's a decaying exponential function. And well, these two at the beginning, in the first term, it's going to tell us that the graph is shifted up 2 units. Okay, so the corresponding f of x so we're going to have this 1, 2, this horizontal asymptote, and shift it up to units. So what are we going to have here? Are we going to have an upper bound or a lower bound? What is this in this case? It's a lower bound, right? So this sequence is bounded below by m, in this case it's little m for upper bounds, right? M equals to 2. So yes, ultimately we're finding a limit just the same way we did it at the beginning of the section, but this time we need to look a bit further and determine whether that limit is an upper limit or a lower limit. That's all it is. What do we have here? Arctan of n pi. All right, so let's write this as a limit problem first. Limit of arctan of pi n as n approaches infinity. And well, where is the arctan function gonna go for positive values of infinity? Infinity. Okay, not quite infinity. Not 1. It was one of those special limits that we discussed back when we covered, what was that? Improper integrals, right? One of those arctan functions at infinity, all right? So what's that?
Pi halves.
What is that? Pi halves, right? So this is pi over 2, right? Pi halves. But now let's have a look at the graph of arctan of x. So y equals arctan of pi x. It doesn't matter if the coefficient is pi or 1, whatever that is. So it looks like this. It has 2 horizontal asymptotes, 1 above and 1 below. But be careful, because just because we have 2 horizontal asymptotes in our graph, it doesn't mean that this is bounded both above and below. It's going to be only bounded above because we're looking in the positive direction of infinity. In fact, we don't care about the negative side or the negative tail of the graph of the function. So we just consider that part for which we have an upper bound. So bounded above by big M equals pi over 2. Alright. Let's have a look at the next one. Okay, so letter C. Sine pi halves over n, pi halves n rather. So let's write it down as a limit problem. Limit sine pi over 2 n as n approaches infinity. Alright. Well, so what's going to happen? Well, number one, how about we'll list some of the terms of the sequence in this case, because, well, for n equals 1, that'll be sine of pi over 2. But what's sine of pi over 2? 1. Well, so that's going to be 1. Okay, n equals to 2, that'll be sine of pi. What's sine of pi? 0. then n equals to 3. What sign of 3 pi over 3 or 3 pi over 2? Yes. Negative 1. And then the pattern continues 0, 1, 0, negative 1, etc. So what is this sequence doing essentially? Well, this sequence is doing the following. So it's doing 1, 0, negative 1, 0, 1, 0, negative 1. So it's oscillating between negative 1 and 1. And it's oscillating forever, whether you consider the negative side and the right side. But in this case, we're just considering the right side of the sequence, all the positive integers in this case, the positive number of terms in this case. So this means that we're going to have a bound at the top and a bound at the bottom. So this sequence is both bounded. We don't have to say it's bounded above and below. We just say it's bounded between negative 1 and 1. And all we have to do here is split this to values like m equals to negative 1, that's the lower value, and big M equal to 1, which is the upper bound. Right? So one example of each, one bounded below, one bounded above, and one that is bounded, just bounded, right? And I believe this concludes the section, so let's move on to the next infinite series. Alright, so we already finished the sequences part. Let's move on to the next part. Series. Okay. So series and sequences are similar in terms of how we obtain their terms. You know, we obtain the first term, the second term, the third term of a sequence in the same way that we do it for a series as well. However, for a way to distinguish a sequence from a series is that the series right here has this uppercase sigma symbol from the alphabet, from the Greek alphabet. All right, this sigma, this letter is called sigma, means to sum. Means sum. So we will be computing sums from 1, to infinity. Well, in this case, we will be looking at infinite sums, not finite sums. You went over finite sums back in pre-calculus or college algebra, depending on the class you took. So this is the notation. And what's different from sequences? Well, in sequences, all we did is list the terms of the sequence separated by commas, but that was it. We didn't do anything else. Maybe just figure out a pattern to write the general rules when we did the backwards problems, you know. But in this case, for series, yes, we'll list the terms of the series. However, in this case, we do an operation with those terms, which in this case is to add those terms, all right? And so here is the thing. With finite series, that was fine whenever you had like a geometric finite series or a geometric or an arithmetic finite series as well. Well, in that case, you were able to add, like the first 7 terms or like the first 759 terms. You didn't have to write 759 terms to add them all together. Actually, there were formulas to just plug in what the first term of the sequence is, what the last term of the sequence, and the total numbers of terms in that case. And it was easy to just plug it in a formula to get that final sum. However, when it comes to adding infinitely many terms, which is possible in at least 2 cases, so only for those cases I will tell you how we're going to add, depending on whether the series converges or diverges. However, in this case, later in the chapter, we will just look at different techniques, at tests to determine whether a series will converge or diverge. So because in many cases it will be practically impossible to find such an infinite sum. All right. So, well, it's possible to write to obtain the infinite sum if we consider a sequence of partial sums. So we are going to have many terms. The first, second, third, etc. S of 1 will denote, well, just A sub 1. That's the first term. S sub 2 will be the addition of the two terms. S sub 3 will be the partial sum of the first three terms. S sub 4 will be the partial sum adding the first four terms, etc. That's the easy part. I mean, we can add numbers together, right? So I don't think that's an issue. But the problem is here that, well, every sum S1, S2, S3, S of n. So we are going to look at all these different sequences of partial sums, and from there try to figure out a pattern, try to obtain an expression in a similar way that we did with the sequences in the previous section. But that's the problem. The problem here is that is not possible all the time. It could practically be impossible to obtain unless you're the mathematicians, Srivansa Ramanujan. Well, so for him it was easy to obtain this infinite series in a blink of an eye, but it's not an easy task. So this is what we will have to do: obtain a sequence, or the general rule of the sum of sequences, and in this case find the limit, and that limit will be the sum. All right. And well, this is the reason that pretty much every calculus book contains like 10 or 12 sections in this chapter. If this task of finding the infinite sum were easy, well, this chapter would have been only 2 sections: sequences and series, and that's it. However, for the sake of simplicity, we will just be caring about whether the series converges or diverges. And for this, we have a bunch of chapters, or rather a bunch of sections, to look at many different kinds of series and their techniques to determine their convergence or divergence. And again, the only ones that will give us the infinite sum are going to be the telescoping series, which we will discuss shortly, and the geometric series. Everything else, don't even try to find the infinite sum because it's not going to be possible. All right. So let's have a look at one example of why is this simply not practical to do. Well, so let's show that the infinite series sigma n equals 1 to infinity 1 over 2 to the n converges. So in this case we're going to find the infinite sum, and no, I'm not going to plug in n equals 1 equals 2 infinitely many terms, because that's not how we do. So number one, I'm going to expand some of the terms. Now notice in this case this 1 over 2 to the n, so we're dealing with powers of 2. So that's so we're going to start with n equals to 1. That's essentially 1 over 2 to the first power, that's just 2, plus 1 over 2 squared, which is 4, that's 1/4, plus 1 over 2 cubed, which is 8, 1 over 2 to the 4th, which is 16, plus 1 over 2 to the 5th, which is 32. Well, I think this is good enough. So you get an idea of what the series looks like. So let's define a pattern of partial sums, all right? Partial sums. So for the partial sums, so I'm going to define S sub 1. So this S sub 1 is the sum of only the first term. Well, there's really nothing to add. It's just saying S sub 1 equals the first term. How about S sub 2? S sub 2 is the addition of the first two terms, 1/2 plus 1/4. All right, and combining like terms, finding LCDs. Well, I really don't want to spend too much time finding LCDs. I'm just going to give you the answer to this. Well, this is going to add up to 3/4. All right. And well, S sub 3. That's going to be the addition of the first three terms. In this case, that's 1/2 plus 1/4 plus 1/8 equals, well, after finding least common denominators, combining the fractions together, this should add up to the quantity 7/8. 7/8. S sub 4, that's the fourth partial sum. That is, adding the first four terms. In this case, 1/2 plus 1/4 plus 1/8 plus 1/16. And after combining these numbers, finding least common denominators and all that, this should be 15/16. All right? And well, we can continue on and on, but I think 4 partial sums is going to be good enough to find our sequence here. So we're going to define S sub n. So let's define S sub n, that is the sum of the n number of partial sums. Well, I didn't do infinitely many partial sums. I just did 4 of them. So let me do S sub 1 plus S sub 2 plus S sub 3 plus S sub 4 plus, goes on forever, goes on forever, infinitely many partial sums. So I'm going to write down the results that I obtained in the previous step when we define those partial sums. So S of n equals to 1/2 plus 3/4 plus 7/8 plus 15/16 plus ... Well, this pattern goes on forever. And again, with these 4 terms, I think this is good. This is a decent amount of information to come up with an actual sequence. Okay, so here is where we will have to use our pattern recognition. So do you notice anything that we can generalize to, an expression that generates that sequence or that sum rather? And if so, what would that be? So do you recognize the pattern of numbers in the denominator? What are they? They're powers of 2. So that means 2 to the n, all right? But what about the numbers in the numerator? 1, 3, 7, 15. N plus 2. Well, n plus 2 would work for the second term, right? I mean, if we start the sequence at 0, well, that'll be 1 in this case, and it's not going to be. And even for n equals 1, okay, yes, that's going to give us the 3 in the numerator, which is only the second. So the n plus 1, it's not going to work. 2 to the n minus 1, because if you look at these numbers in the numerator right here, so this is basically 2 minus 1. This is 4 minus 1, this is 8 minus 1, this is 16 minus 1, and those numbers 2, 4, 8, 16 are the same numbers in the denominator, right? So this is the reason why we don't do this for every single series, because I mean this one it has a decent challenge to do, but I mean there's other series that this task it's simply impossible to perform. So for this reason, for many kinds of series, we will just care about the convergence or the divergence without looking at the infinite sum. Yes?
Do we always use just 4 examples, or do we want?
Yes, 4 or 5 or even 3. Even with 3 might be enough, but typically a good amount is for sums. Well, so let's find the limit. The limit n approaches infinity of 2 to the n minus 1. And by the way, the minus 1 it's subtracting from the 2 to the n. It's not in the power, all right? Over 2 to the n. Well, to calculate this limit, well, we would need direct substitution. We would get the, what's it called? Infinity over infinity indeterminate form. So that means we can do some algebra. And there's a couple of ways to go about this limit. L'Hopital's rule actually would cancel the exponential terms, or without even taking any derivatives. How about Limit n approaches infinity, that's 2 to the n over 2 to the n minus 1 over 2 to the n. And well, this will be limit of 1 minus 1 over 2 to the n approaches infinity. And well, where is 2 to the n going to when we it's going to go to 0, and 0 plus 1 equals to 1. What does that result mean anyway? This is the result of keeping adding 1 over 64 plus 1 over 128 plus 1 over 256 plus infinitely many terms. This is equal to 1. Alright? But again, I mean, and this is like one of the simplest or the easiest series ever. And look at the amount of work that we had to do just to get this simple result, right? So again, that's why we're just going to care about the convergence or divergence, but not really about the result of the infinite sum. All right, so let's look at the first kind of series, the telescoping series. Well, a telescoping series is a series of the form b1 minus b2 plus b2 minus b3 plus b3 minus b4 plus b4 minus b5, etc. This pattern continues. So essentially, well, it's like having a telescope, right? You are at the initial point, and you have the telescope, and all you're looking is your objective at, I don't know, maybe 25 miles away, right? But you don't care about everything that it's in between. So because actually this gets canceled, infinite, and all you care is the initial term and the last term. And this series right here, you are usually have the form of rational expressions in their rules. In some cases, they might be nice to you and give you the series like this with the sum, or rather the difference of the rational expressions. But in some cases, you will have to do the process of partial fraction decomposition. So let's see what happens here. All right. So let me write down the series again. Sigma n equals 1 to infinity, and that's 1 over n minus 1 over n plus 1. Alright, so we're going to expand a few terms. So maybe how many? Maybe 4. Alright, so I'm going to do, so for n equals to 1, let me denote it here, n equals to 1, I'm going to write down 1 over 1 minus 1 over 1 plus 1, which is 2. Plus, for n equals to 2, I'm going to do 1 over 2 minus 1 over 2 plus 1, which is actually 3. Plus, for n equals to 3, that's 1 over 3 plus 1 over 3 plus 1, which is 4. Plus, for n equals to 4, that's 1/4 minus, or actually this one is supposed to be minus 1 over 4 plus 1, which is 1/5. But I mean, we don't need to have infinitely many terms in here. All right. So in this case, if the sum continues on and on, eventually we will get the following. So okay, I'm going to continue the sum here. Plus, okay, so let's suppose I did infinitely many terms between, so I'm denoting these infinitely many terms using these triple dots right here. So that's going to give us, okay, I'm going to leave some space here, the nth term. And the nth term will be given by 1 over n minus 1 over n plus 1. All right? That means that the second to the last term will be 1 over n minus 1 over n. So this is what's going to happen. So check how this negative 1/2 cancels the positive 1/2. the negative 1/3 cancels the positive 1/3, the negative 1/4 cancels the 1/4, the negative 1/5 would cancel the positive 1/5 in the next term, and see how this pattern, this cancellation pattern continues, and in this case cancel 1/n minus 1/n. And well, what are the terms that survive the cancellation? It's the initial term and the final term. Again, that's why we call it the telescoping series, because it's like using a telescope. You have the telescope, you are the initial term, and the objective is essentially the final term in this case, or the nth term right here. So this means this is equal to 1 minus 1/n plus 1. So in this case, this is essentially a sequence of partial sums, if you will. But notice how this special case of partial sums cancels many of the terms in here, leaving us only with the first and the last. All right? In this case, we didn't have to figure out a pattern like the one in the previous case, in which we had to get that 2 to the n minus 1 divided by 2 to the n to then find that limit. So we may go ahead and find this is s of n. So let's find the limit of s of n and approaches infinity. So this is limit of 1 minus 1/n plus 1 as n approaches infinity. Well, so as usual, this term is going to go to 0, because that's essentially 1/infinity plus 1. It's still infinity. 1 over really big is 0, and the infinite sum is 1. All right. So that was one example of the telescoping series. Let's look at another kind of series. And again, in some cases, they could be nice and give you the problem like this with actually the rational expressions expanded. But in some cases, you would have to do some partial fraction decomposition first to get this expression, and then do this telescoping sum. All right. The geometric series. So a geometric series, it's distinguished by having all of its terms having a common ratio. For example, the number or the sequence 2, 4, 8, 16, 32, etc. is distinguished because every consecutive term, it has a common ratio with its previous one. So what do we get when we divide 4/2? What do we get when we divide 8/4? 16/8. 32/16. So we have a common ratio here. All right. So that means this is a geometric progression, or a geometric sequence. Well, we're not looking at sequences anymore. In this case, we're looking at the series. We're going to look at the geometric series, which has this form. Well, this A right here represents the initial term of the sequence, or the first term of the sequence, well, that will later be added by this sum, and well, this R is that common ratio, because this is what we have essentially. So 2 times the common ratio 2 to the 0, comma 2 times 2 to the first power, comma 2 times 2 to the second power, 2 times 2 to the third power, 2 times 2 to the fourth power. This pattern continues here. So in this case, see how this common ratio right here, it's essentially this R to the n, and that depends on whether we're working with the 0th term, the first term, the second term, etc. All right. So that's the form of a geometric series with a numerical example. But be careful here. Be careful when working with geometric series. So check this out, and you might want to highlight this. Put a star. This is important. Because if you don't make sure that the series, so the geometric series, must start at n equals to 0. If you are working with a series that does not start at n equals to 0 and you compute the infinite sum, you're going to get a mistaken result. So you want to make sure that your series starts at 1. Whenever the series starts at a different index, well, I'll let you know in maybe not today, maybe next time I'll let you know what do we do in such cases, okay? So we're going to do something called shifting of indices, and that's something important that will be required to do later in your courses, like differential equations or complex analysis, other numerical analysis courses as well. So let's have a look at some examples. Oh, well, before looking at the example, so we have to go either one way or the other, one direction or the other. Well, number one, we have to identify R, the common ratio, and if the absolute value of that numerical value is less than 1, well, the geometric series converges, and in this case it's possible to find the infinite sum using this formula, S subscript infinity A over 1 minus R, where A is the first term of the series and R is the common ratio. But otherwise, if the absolute value of R, the common ratio, is a number greater than or equal to 1, well, the geometric series diverges and you're done. You don't have to do anything else. Okay, let's have a look at some examples. So number one, we have the sigma n equals 0 to infinity 1 over 2 to the n. Okay. So let's see. Number one, we need to write the series in the form AR to the n. Unfortunately, it's not yet in that form. But we're going to do some manipulation, a really basic manipulation, nothing crazy. Sigma, oh, come on. N equals 0 to infinity. And this 1 over 2 to the n, isn't it the same as saying 1 over 2 whole quantity to the n power? Because, well, 1 to the n is simply 1, and to do the n is to do the n. And, well, I left a space on purpose just so we can identify that we have an invisible 1 in there. So now our series, our original series, has the form sigma n equals 0 to infinity A R to the n power, as the one that we have in the definition box. Alright, so this is what we have to do. Number one, identify the parameters in this case. This is a sub 1, or rather just a, not a sub 1, just a, which equals to 1, and R equals to 1/2. So now that we identified these two parameters, we have to go, we can go ahead and perform the test. So in this case, absolute value of R, which equals absolute value of 1/2. So what is the absolute value of 1/2? Isn't it just 1/2? Now we need to look at this number. 1/2 is 1/2 less than 1 or greater than or equal to 1? It's less than 1. Okay, since this number is less than 1, what would we say? The series converges or the series diverges? Series converges. And in this case, it's possible to find that infinite sum using this formula, so which I'm going to do up here. So S sub infinity equals A over 1 minus R, and all we do is plug in these two numbers based on what we identified at the beginning of the exercise. All we do is plug in A, which is 1, over 1 minus R, which is 1/2. So what is 1/2 minus 1/2? Isn't that 1/2? And, well, what's 1 over 1/2? That's 2. So that means that infinite sum equals to 2. All right? let's see. Let's look at letter B. So for letter B, we already have the series in the desired form. That is a r to the n power. All right. So number one, let's identify the parameters. Those parameters are a, which is 3, and from here r equals to 5/2. And well, so number one, judging the r, that is, take the absolute value of r, which is the absolute value of 5/2, which is 5/2. But that number 5/2, is that less than 1 or greater than or equal to 1? So greater than or equal to 1, which means diverges in this case. And in this case, we're done with the series. There's nothing else, because the fact that the series diverges, that's telling us that the infinite sum is infinity, just blows up to infinity. So we're done with this one. All right. Okay, for the previous example, that reminded me of a mathematical joke. You may have heard it before. So there's a mathematician walking into a bar and asks for a beer. And then a second mathematician asks for half of a beer. Then a third mathematician asks for a quarter of the beer. And then, so the bartender kind of figures out the pattern, and all he does is serves 2 beers for infinitely many people getting into the bar, all right? And well, the next topic, shifting indices, I think I'd rather do it next time. So